Okay, good morning to everybody, and thanks, Bruce, for hosting this session, and of course, thanks to the organizing committee for inviting me. Today, what I would like to speak about is a vision of how predictive medicine could evolve through the exploitation of advanced artificial intelligence, and in particular through innovative architectures derived from neuroscience. Predictive medicine is a field of medicine that aims of identifying patients that risk of developing a particular disease. In a certain sense, this definition could have been employed to describe medical professions since Hippocrates. However, the advent of advanced computational mathematical tools like deep learning or machine learning and the availability of high-performance computing boosted the exponential growth of the applications of predictive medicine in the healthcare systems. Since the ancient Greece, the process of medical intervention is made of serial steps, from the appearance of symptoms of a particular disease passing through an attempted diagnosis and a proposed therapy to reach a hopefully positive outcome. In the last century, however, the development of a wide range of new technologies applied to health and medicine started to parallelize a bit the steps of getting to the outcome. In particular, imaging or in vitro diagnostic allowed to tailor targeted therapeutic interventions in order to obtain positive outcome with a higher probability. And then the parallelization process has been further expanded thanks to a wide series of tools, from genomic and genetic profiling to artificial intelligence algorithms. And much of the efforts has been devoted to the increase of the type and number of devices to be used to collect data in order to monitor patients and to create preventive and targeted therapies. It is thus clear that predictive medicine represents one of the main achievements for the future of every healthcare system, which is one of the main indexes of the quality of life in a society, since predictive medicine can take us to an increased and improve, and of course, more diffuse prevention. And then, of course, prediction means eliminating adverse events once a therapy started. These aspects can lead us to a better healthcare system, which in turn means to increase life expectancy. In a broader sense, being capable of accurate and tailored prediction can speed up the process of translation to market of newly developed drugs or vaccines with obvious consequences on everybody's lives, as we had experiences, unfortunately, during these months with the recent pandemic. But given these premises, where are we now, and what do we need to further improve predictive medicine? Well, there are several things that are necessary to define a global strategy for an efficient predictive medicine. On one hand, genetics profiling and genomic, together with advanced informatic tools like bioinformatics, in order to analyze and to manage data, I'm quite sure will become the gold standard in the preliminary steps that lead to the diagnosis and to the optimal therapeutic intervention. On the other hand, of course, it's necessary to further improve technologies applied to medical field, as well as increasing the number of medical devices is necessary. And both of these improvements will bring us to a more personalized and molecular diagnostic. Of course, not less important are the data protection and management of the huge amount of data coming from all those devices and new technology developed for predictive medicine, and the property and the protection of personal data is a key aspect that has to be taken into account for a safe and reliable predictive medicine and e-health. There are, of course, a few issues that has to be faced to achieve these targets. Of course, the first is the way we manage the huge amount of data that are collected by devices, whether they are wearable or not. And these devices can be adopted in several ways and can capture significant data which are fundamental to prepare appropriate and to generate accurate diagnosis. And these data are quite commonly of different types. The second issue is, of course, closely to the first one, but is related to the management of this data and to how analyze and manage those data. At the moment, this big data analysis and management is performed through cloud computing, since high-performance computing are not yet portable, and most importantly, high-performing computing is poorly energy efficient. So how could we overcome these limitations that at the moment seem intractable? One hint comes straight from the nature, since the most powerful computational engine that can perform parallel operations with a very limited power consumption is the human brain, and in a broader sense, the nervous system. As in the case of the development of artificial neural networks, where some of the features of the human brain architectures have been mimicked to improve computational performances, the analysis of brain functions can provide us inspiration on how to face the problems of managing big data while keeping the energy consumption as low as possible. The human brain, in fact, can analyze in real time information coming from billions of receptors throughout the inner and outer surfaces of the body. For instance, more than 100 million photoreceptors collect photons incoming to each of the two retinas to generate signals for a continuous stream of images to be integrated by cortical brain areas with signals coming from other types of receptors, generating an efficient body perception and, in a broader sense, generating cognition. Well, actually, the idea to draw inspiration from brain capabilities to improve the performances of artificial machines is not new. However, there's a recent theory by which brain can act as a predictive engine. It has been in fact proposed that brain collects inputs from external sources, for instance, receptors, not just to react to those inputs, but rather to compare them to an internal model of the world that is generated and continuously adapted to the sensory signals collected from the environment. So brain can be considered as a perfect predictive engine, provided with an internal model of the world described by a series of hidden causes that subtend the sensory evidence collected from receptors. This vision of the brain can be extended to predictive medicine, since it has the potential to solve all the issues that we mentioned in a couple of slides ago at the same time. It treats huge data, it is computationally efficient, and most importantly is low power. So now, more than ever, understanding and modeling brain complexity can provide us effective tools for the understanding of complex problems like predictive medicine. And that is what we are trying to do during these last couple of years. So beside the parallelization and the increase of computing performances, brain-derived computation needs not only algorithms or new computational paradigms, but also different types of hardware to manage big data while preserving the energetic efficiency. These types of hardware mimic neuronal and synaptic functions and can be organized as neural circuits to reproduce brain behavior on one side and to operate as brain in silico and perform complex tasks on the other side. So beside the direct advantage of fast computation and low power consumption, these architectures can remove the weight of performing lots of calculation and big data management from cloud, which is very energy expensive. For instance, it has been estimated that 1 hour of Google search on your machine can produce approximately the equivalent in carbon dioxide of 1 liter of gasoline of your cars. So shifting from cloud to onboard, the computation have several advantages. Among them, the speed, so calculation can be performed in real time without exploiting the 4 or 5G speed of connections, and of course it's sustainable. The most brilliant application of these paradigms is the Human Brain Project, which has the aim of creating a digital twin of the human brain to be used for medical, pharmaceutical, and robotics application. Among all the targets that are pursued by the project, some of them are particularly tied to the topic of predictive medicine. For instance, sharing data on neurons and synapses to better understand our brain functions. And of course, reconstructing brain architectures to perform brain simulations, to simulate how the brain works and explore some pathological conditions, for instance. HBP is also devoted to improve high-performance computing analytics and to allow diffuse access data on patients and on most of the identified brain diseases, and to implement advanced neurorobotics for neural rehabilitations, and of course to develop and implement advanced neuromorphic computing strategies. For instance, in one of the human brain sub-projects, which we are coordinating in Unimore, we are collecting data on neuronal morphologies from patients suffering for epileptic disease to reconstruct a network of human hippocampus to be used to simulate the functions and dysfunction of hippocampal circuits, and to therefore develop alternative therapeutic strategies in order to get to the new generation of predictive medicine. I hope I was within the time window.